With the advent of the 21st century, the search for solutions to the looming energy crisis has been a massive endeavor. All over the world, scientists have worked towards developing potential technologies for clean, renewable, and safe energy. The holy grail of this research would be harnessing the power of nuclear fusion. Fusion is the process under which, under certain conditions, atoms like isotopes of hydrogen or helium can come together and fuse, releasing large amounts of energy. If done correctly, you could theoretically contain a fusion reaction under high enough pressure, with fuels that are abundant on Earth, and reap the benefits of energy released by fusing the atoms. This isn't just some hypothetical nonsense dreamt up by scientists either, as nuclear fusion is none other than the mechanism that powers our sun, and releases all the light, heat, and energy we receive on the surface of the Earth. Nearly all forms of renewable energy on Earth rely on recapturing just a tiny fraction of that fusion energy. The largest barrier to achieving a sustained fusion reaction, however, are the conditions required. Scientists need to contain an environment just like that of the core of the Sun, on a planet. This means finding a way to hold plasma that is tens of millions of degrees Celsius. Any kind of heat leakage or contact with materials to contain it would simply drain energy from the system, and at that temperature vaporize the surroundings.
I'm afraid we'll be deviating a bit from standard analysis procedures today, Gordon.
Though it would quickly dissipate without a proper environment, since this doesn't pose much of a hazard.
I am a goner!
Any energy drained or lost means we have to put in more containing it than we get out. So, if you can't contain plasma this hot with walls or conventional storage, how could we possibly do it? This brings us to the point of this entire presentation: magnetic confinement fusion. Magnetic confinement fusion is a relatively new technology, first implemented by Soviet scientists in the 1960s. As of today, MCF is the most feasible known method for fusion confinement. The basic principle is using extremely powerful magnetic fields to act upon the charged particles inside of a superheated plasma and confine it to a small space. An example of a similar effect in nature would be
Good Lord, what is happening in there?
Aurora Borealis and Australis.
God save the Queen!
That being, large amounts of plasma confined to strips of Earth's magnetic field high up in the atmosphere. The shape of a conventional modern fusion reactor is a specialized torus known as a tokamak. This donut-shaped reactor is designed around the very shape of a magnetic field, because it applies its magnetic forces on the plasma in such a way that it spirals along with the field rather than expanding outwards. Here, I'll try to explain. To demonstrate a basic example of magnetic confinement, let's draw a uniform magnetic field. You can see a few magnetic field lines like this. What happens if an electron is shot into this field? Based on a lot of math and some point charge physics, we actually know that with a significant enough velocity and decent angle, it might start orbiting like this, and unless acted upon, a point charge would attempt to orbit these infinitely thin lines on a magnetic field forever. With some velocity this way, parallel to the magnetic field, the particle is going to orbit, and as it orbits, it's going to travel down the magnetic field lines. In a tokamak, magnetic field lines are set up to orbit around the torus through the use of many coils in its surface. Many thin slices of electromagnetic solenoids control the flow of charged plasma, though plasma is routed around and around in a circle. This is obviously a very oversimplified look at the subject, as much of the details in the realm of advanced nuclear physics. In the resources I've found, the primary force acting upon charged particles for magnetic confinement is the Lorentz force, with an illustration from Penn State University above. The Lorentz force is defined as F equals QVB, where B is measured in teslas, the strength of magnetic induction and field at a given point. Tesla can be simplified into other SI units as shown above. The force F is perpendicular to the direction of the magnetic field B, and it is also perpendicular to the direction of velocity v. F is perpendicular to the plane that contains both v and b. Orbital mechanics aside, this one physical force explains a fair amount of the macroscopic behavior of charged particles with magnetic fields. Charged particles will follow along a magnetic field because of the Lorentz force. Lorentz forces, Ampere's law, and the Lawson criterion were some of the many other physics concepts employed in designing fusion reactors. To address the elephant in the room, why are magnets used for fusion reactors? And are there any other known techniques? There's actually one other well-known technique for containing plasma, known as inertial confinement fusion. Inertial confinement fusion, or ICF, initiates nuclear fusion reactions by heating and compressing a fuel target, typically in the form of a pellet that most often contains a mixture of deuterium and tritium. This is known as a ha-ha-rom. To start this reaction, a beam of extremely high-energy lasers, ions, or electrons is fired at the pellet. The pellet explodes outwards and compresses inward. Shockwaves generated by the machine strike the target, further compressing the pellet and generating the conditions for fusion via inertia and physical compression. One of the main reasons this method has seen less research over the past few years is its rapidity and low efficiency. The power needed to set off a tiny explosion and shockwaves capable of generating fusion required much more energy than was feasible for the purposes of generation. Not only that, but the energy transfer in ICF reactors takes place over the course of milliseconds at maximum, whereas a tokamak can be fine-tuned and adjusted for much longer periods of time. This short clip by George Chaniottakis demonstrates the effects of magnetism on a charged plasma very clearly, as well as showing clearly defined magnetic field lines. This is footage of a homemade plasma chamber with large permanent neodymium magnet inside. And we're at the end. I hope you learned something interesting from my presentation about fusion and magnetism, and hopefully one day we'll see this mechanism used for generating our power every day. Thank you for watching!